Hey guys, I think that some of you are confused by the Minimax algorithm and probably a lot of you are confused by alphabet pruning. There's a lot of technical explanations of both of those concepts online, but they can be a little bit hard to understand, so I'm going to try and give you a more intuitive understanding of Minimax, alphabet pruning, how they work and why they work. If you already understand Minimax, you might want to skip ahead to the alpha beta pruning bit. Okay, so before I start to explain Minimax, there are a few concepts that I need to explain first. So the first concept I want to explain is that of a game tree. So you know a little bit about trees. A game tree represents different states that a game can be in. And those states might be the positions of different chess pieces on the chessboard, or the positions of the different chips in the Connect 4 game, for example. So each of these states can be represented by a node, and in each of these states there'll be a certain person whose turn it is. And they will have a number of moves that they can make, and that number usually isn't the same from state to state. Sometimes you'll have 5 possible moves, sometimes you'll have 10 possible moves. And the new states that are reached when you make each of those possible moves are represented as the children nodes of that first initial node, and etc. etc. The second concept that I need to talk about is the concept of a zero-sum game. So a zero-sum game means that if you better your position, that means that your opponent's position is worse. So there's no scenario where you can collaborate with your opponent. So in a zero-sum game, your opponent is always going to minimize your score, because minimizing your score will maximize their score. And the third concept I want to talk about is the concept of a heuristic. So in this example that I've got on the screen here, each possible state has 3 moves that you can take. And that's probably a lot less than you're going to find in most games. And you can see already, even with just 3 moves per state, even at a depth of 1, 2, 3, it's growing pretty fast. And game trees do grow extremely fast. So you can rarely ever, unless you're towards the end of the game, explore the whole game tree right until the end. So you need to cut off at a certain point. And the point that you cut off at is probably not going to be either a win for you or a loss for you. So you need some way of assessing whether or not that's the state that you want to go towards. And you do that by using a heuristic. And a heuristic is an educated guess about how far away that state is from a goal state. And in this case, the goal state will be a state where you are the winner. So as far as heuristics go, the basic and reliable one is just something like your score minus their score. It's possible to come up with more advanced and complex heuristics, but generally, if you want to do that, you need a bit of knowledge about the game that you're playing. And if you don't have that knowledge, sometimes it's a bit risky to try and come up with a different heuristic, because if you get it wrong, you won't be performing, because you won't be able to find good states with any degree of accuracy or reliability. Okay, so now that we've got those concepts out of the way, I can start to explain what Minimax actually is. So Minimax is a way of determining, if we're in this state, which of these possible moves is the best one to take. And we do this by generating a game tree to a certain depth and then evaluating the states at the bottom through your heuristic. So these are the heuristic values for each of the states at the bottom. The upward arrow, the upward triangle, indicates a node where it's your turn, so you can choose which path to take, and the downward arrow represents a node where it's your opponent's turn, and they can choose which path to take. So this next layer up, we can see that it's an upward pointing arrow. So take this one for example. If you're in this state, you have a choice between going to a state with a heuristic value of 12, or a heuristic value of 13, or a heuristic value of -11. Now remember that the higher the heuristic value, the closer you are to the goal state. So if you were in this position, you would want to take the middle path, which would lead you to a state with a heuristic value of 13. And because a path exists from this node to a state where the heuristic value is 13, we can say that this node also has a value of 13. And we can find the values of each of these bottom nodes simply by looking at the possible choices that that node will have and picking the highest one, because it's your choice, and if you're in that position, you're going to choose the path that gives you the best score. Now over here we've got -15, -1, and -3. Now these choices aren't really that great, but if we do find ourselves in this position, we will still need to pick the best one, and the best one in this case is -1. So we can say that this node has a value of -1, because if we're in this node, we can get to a state with -1. So I'll just go through and fill out a few more of these. So this one, have a think about what you think the value of this node will be. Will it be 7, 11, or -6? Well, it's your decision, and you want to maximize the score, so it will be 11. Over here we've got 12 and 17, and then 10, and then 17 again, and then 15, and then 13. Okay, so that's how you calculate the value of what we call these maximizing nodes, because they're nodes that pick the maximum value of their children nodes and inherit that as their value. Now we can move on to minimizing nodes, and they're called minimizing nodes because these nodes represent a state where it's your opponent's turn. And because it's a zero-sum game, your opponent is trying to minimize your score to maximize their own score. So if your opponent finds himself in this position, they know that taking this path will put you in a position where you can get a 13. They know that taking this path will put you in a position where the best you can do is a -1. And they know that this path will put you in a position where the best you can do is 11. Now, if they have these three choices of which score that they want to allow you to have, they're going to choose the lowest. In this case, that's -1. In this case, they have a choice between allowing you to have 12, allowing you to have 17, or allowing you to have 10. So the lowest value here is 10, and that's the one that they're going to take, because they don't want to let you have 17, and they don't want to let you have 12. 10's still alright relative to the other options, but it's the worst one that this current node has access to. So we'll put a 10 in here. And the same here with 13. So just to recap, the maximizing nodes, the ones that represent states in which it's your turn, their value becomes the highest value of their children. So they will look through their children and find the one with the highest value and take that as their value. The minimizing nodes do the opposite. They look through their children, which are these maximizing nodes, and they pick the lowest one. So they're trying to put you in the worst position that they can. Okay, and they alternate. So once we've figured out the values of these minimizing nodes, these values representing the best value that they will allow you to take if they find themselves in that position, we can then move up to this top node. We can say, okay, we're in this position, we're in this game state, it's our choice which path to take. If we take this path, our opponent will put us in a position where the best we can get is -1. If we take this path, our opponent will put us in a position where the best we can get is a 10. And if we take this path, our opponent will put us in a position where the best we can get is 13. So we can see now that it's best to take this path. Because if we take this path, what we're doing is we're kind of taking away the ability of our opponent to decrease our score. Because the only really negative scores on this part of the branch contain a path to a really high score, and that path is our decision. So there's no way that they can lock us into a bad decision, because there's a good decision on each of these 3 nodes. And because this is a maximizing node, it's going to pick the maximum of its children, and the maximum is 13. And it will conclude that this is the best path to take. And that's the Minimax algorithm. And the reason it's called Minimax is because you alternate between maximizing nodes and minimizing nodes each step as you build up. You try to you pick the maximum of the node's children, and then you pick the minimum of those children, and then you pick the maximum of those children. So it's constantly switching between minimum and maximum. And there's a reason behind that, which I hope that you understand. Now we can talk about alpha beta. So let's just get rid of this one for a second. Okay, and we'll get rid of these two. Okay, so we're pretending that we've only explored this part of the tree. Okay, so we go down here and we're checking the children of this node, and we're trying to maximize the children of this node. So the first thing that we come across is a 7. So we can preemptively assign a value of 7. Okay, so we can do this because 7 is a possible option. Now we can update it later as we explore more of the children. So as we explore the 11, we can say, okay, well 11 is higher than 7. So obviously we would want to pick that one. And then we would change this to an 11. And then we would explore -6, and we'd say, okay, well that's not higher than 11, so we're not going to update that value. But before we do that, what we can notice is that the value of this node is going to be 7 or higher. And the reason it's going to be 7 or higher is it's already got a 7, and it's a maximizing node. So these values, if they're less than 7, if either of them is less than 7, that value will not be chosen by the maximizing node. If they're more than 7, then that value will be chosen by the maximizing node, because it's going to pick the maximum. So after exploring just this one node, we know that the value of this node is going to be at least 7. Now, is it actually worth exploring any more of these nodes? Well, we know that this is a minimizing node. Okay, so after we've explored this -1, we know that the value that this node will pick is going to be -1 or less. Okay, and it's for the same reasoning as that we concluded that the value of this node will be 7 or more. It's just in reverse. So this node is going to pick the minimum of its children. So the minimum that it's observed so far is a -1. And it knows that the value of this node, when it's been evaluated, if it's higher than -1, it's going to ignore it. If it's lower than -1, it's going to pick this node. So as soon as we run into a position where we can conclude that the value of this node is going to be 7 or more, which we already have, none of those possible values are going to be -1 or less. So we know that already, even after just exploring this one child node, that we don't need to explore these other two. So we can eliminate them. Now the reason we eliminate them is because, as I was saying earlier, game trees can get complicated quite quickly. So if you can cut down on the number of branches you need to explore without cutting out, potentially optimal solutions, you'll be able to explore the game tree a lot deeper and a lot quicker, which will mean that you'll be able to think more steps ahead of your opponent. Yes, so we need a way to generalize this so that every time we explore a node, we know whether the value that it gives us is a value which is okay and which we can keep exploring the children of that node or subsequent children of those children, or a value which will mean that that entire branch can just be eliminated. And we do that by passing down values called alpha and beta. So the alpha value represents the best possible move that the maximizing nodes can take. And the beta move represents the worst possible move in that branch that the minimizing nodes can take. Now this probably doesn't make too much sense to you right now. It will probably take maybe you need to rewatch the video a few times after I explain it to fully understand it. It's also probably a good idea to work through a few examples. This website's actually really good. Once you actually understand or start to understand the concept, it's a really good resource to kind of test your knowledge, because it allows you to fill out the Minimax tree and it will show you which well, you can also click on these branches to indicate that they're not to be explored, and it will you can click on the show solution button, which will show you the alpha and beta level values for each node. But don't worry about that for yet, just wait until after the video, and yeah, then it will hopefully allow you to kind of solidify your knowledge of it. Okay, so we need two values, alpha and beta. Now, when we start running the Minimax algorithm on this original node for the first time, we don't really know what the best or the worst possible values can be. So we choose something called infinity, and it doesn't have to be infinity. Sometimes it's impossible to represent infinity in a programming language. So it just means that we need to pick a number that is high enough such that it won't preemptively cut off any solutions before we've actually explored anything. So if you know that the scores for your game will range between -100 and 100, you could pick anything over 100 or a -100 as your alpha and beta values. It's just got to be, make sure you're not, preemptively cutting off any values which might be explored. Okay, so up on this top level, when we just start, the alpha value starts at -infinity, and the beta value starts at +infinity. Okay, so it doesn't look like there's a way for me to add the alpha and beta values for you to see. So I will just discuss them. Okay, so each node passes down its alpha and beta values to its children. So it will pass down -infinity and +infinity to this node, and that it will pass the same values down to this node. Now, if it's a maximizing node, what it's going to be doing is it's going to be trying to push the value of alpha up. So every time it checks one of its children, it will compare the value of that to the value of alpha that it already has, and it will choose the maximum of those two values to become its new alpha value. So here we have, it will set the first thing that when you first start exploring it, it will have its alpha value will be -infinity and its beta value will be infinity. After you check this first child, you can say, okay, is this value greater than the alpha value that it already has? And the alpha value that it already has is -infinity. So the answer is yes. So you update this value. So 12 becomes the new alpha value, and infinity remains the beta value. And then you check this next branch, and you see that 13 is actually higher than the alpha value, this updated alpha value, which is 12. And so the alpha value for this node gets updated yet again. And beta remains the same. These maximizing nodes don't actually change beta. They only change alpha. And the reverse is true for the minimizing nodes. They only change beta, they don't change alpha. Okay, so we have an alpha value of 13 and a beta value of infinity. And we check this -11, and it's not higher than the current alpha value, so we don't update it. And now what we do, so the maximizing nodes update alpha, they continually try and push it upwards, and then when they're finished evaluating, they return their alpha value. So they will return 13. And I think that we can actually step through this. Okay, so it starts at -infinity, +infinity, passes that down, explores 12, updates alpha to 12, explores 13, and then because 13 is higher, it pushes the alpha value up to 13. Explores -11, but because -11 isn't going to push up the value of alpha, it just stays the same. Then it will return its value. Its value is 13. Now, probably the most difficult thing to understand about alpha beta is the fact that the maximizing nodes return their alpha value, to their parent nodes. But the parent nodes, because they're minimizing nodes, they are updating their beta value. Okay? So they're trying to push their beta value down. Okay? So they will compare the result. They will compare the value they get from each of their children against their current beta value, and they'll check which one's smaller, and they will update their new beta value to be the smaller of the two. So because this node is passing up at 13, and 13 is smaller than infinity, this node will have its beta value updated to 13. I think that's probably the hardest thing to get your head around, because in this node, 13 is the alpha value, and then as soon as it goes up one level, it suddenly becomes the beta value, and the alpha value is still negative infinity. And I think the best way to think about it is that the maximizing nodes change their alpha values, and even though they pass up their alpha values, if you think of it more as just passing up the value that that node takes, rather than that value being an alpha value, it might make it kind of easier to understand why it's updating the beta value here. Because, as I said before, the maximizing nodes are trying to push up the alpha value based on the results of their children. The minimizing nodes are trying to push down the beta value. So it's updating the beta value. And I haven't yet told you why this is useful, or how this is useful. But we should get to it within this next branch here. But let's continue. Okay, so this beta value will be updated to 13 because 13 is smaller than infinity. Yes, and so it passes down these values, passes down its own alpha and its own beta to its child. And now this child goes through the same process that this child did. It tries to push up the alpha value. So it will explore this value first, this node first, and because negative 15 is larger than negative infinity, it will push up the alpha value to negative 15. And the same will happen when it explores this node, which is negative 1. Exploring that node will allow it to push the alpha value up further, so the new alpha value will be negative 1. Negative 3 won't really improve the situation. It's not higher than negative 1, so it's not going to allow the maximizing node to push that value up, so it's just going to stay at negative 1. Okay, now if we can forget about negative 1 being the alpha value for a second and just consider it the value of this node, we will see that this maximizing node will return a value of negative 1 to its parent. And because its parent is a minimizing node, it's trying to push down the beta value. Okay, the beta value is currently 13, but if it accepts this negative 1, we can push it down even further to negative 1. And that's what will happen. It will update this beta value to become negative 1. And again, it will pass down these values. Alpha still hasn't been updated. In fact, alpha won't be updated in this branch. It will only be updated in these next branches. So it passes down its alpha and its beta value. And we can go through the same checking process. We can push up the alpha value by exploring the nodes. So we first explore this node, which is the 7. And since 7 is higher than negative infinity, the maximizing node will push up the alpha value to 7. Okay, now something interesting happens here. The alpha and the range between the alpha and the beta represents the range of possible that the currently explored branch can take. If the alpha value at any point is equal to or higher than the beta value, that means that there is no path in the current tree that is worth exploring. So as soon as that happens, you can say, I don't want to explore things any further. Okay? You can, in fact, that's what will happen right now. Yes, it's cut off these two branches. It said that they're not worth exploring. And hopefully that makes a bit of sense to you. As I said a little bit earlier, the minimum value that this node will consider taking, the maximum value this node will consider taking is -1. It's looking for lower values than that. As soon as we know that this node can take on a value that's going to be 7 or higher, and that's what the alpha value represents, it means what's the minimum score that this node can take. Then we can see that this node is not going to be chosen by this node, and so it's not worth exploring. So the alpha value represents the smallest node, the smallest value that this maximizing node can take, and the beta value represents the maximum value that the parent node will consider. So if the alpha value is higher than the beta value, it means that the parent minimizing node won't even consider it, and therefore you shouldn't either, because that game state is never going to be reached. Okay, so this will pass up its value of alpha, which is 7. But since this is a minimizing node here, and the minimizing node is trying to push down the value of beta, it's not going to change because 7 is higher than -1. It won't allow it to reduce the value of beta any further, so it will not update that value. Okay. So now if we look back up here, this is where we're about to return to. The value of alpha up here is still -infinity. And since it's a maximizing node, it's trying to maximize the alpha value by looking at the return values of its children. So the value of this node is -1, so it will return a value of -1, which means that because -1 is a larger number than -infinity, this maximizing node will push up the alpha value to -1. And there you go. So for the first time ever, we have passed down a alpha value which is not -infinity, although the beta value remains infinity, because this node will actually not update the beta value that it passes down. Only the minimizing nodes will update that value. Okay, so we've passed down a value, but we don't know the values of any of the children of this node yet, so we'll pass that down here. Okay, now we'll explore the children of this node. Remembering that because it's a maximizing node, it's looking at its children, it's looking at the values of its children, it's comparing those values to alpha, and it's taking the best as its new alpha value. So here you've got -19. -19 is not higher than -1. Okay, now what does this actually mean? What this actually means is that this node up here knows, okay, there's a potential path that will lead me to a score of -1. Therefore, if I'm going to even consider taking this path, there needs to be a path within here that gives me a score that's higher than the one I already have, which is -1. So because this is like the minimum value that this node up here will consider, it's not going to be updated by this -19. It's not going to be updated by the -3 for the same reason. It's better just to take this path. Okay, but now when we see the 12, the 12 will update this alpha value because it will allow the maximizing node to push up the value of alpha, and remembering that that's what maximizing nodes are trying to do. They're trying to push up the worst possible move that they can make. They're trying to say that, okay, we can get at least -1, but if we can get at least 12, that's even better. So there we go. Alpha has been updated to 12. Now, since the value of this node is 12, that's what will be passed back. And forgetting that in this node, 12 is an alpha value, and just thinking of it as a return value, and remembering that because this is a minimizing node, it's trying to push down the value of beta. It will compare the value of infinity, which is the current beta, with the value of its child, which is 12, and it will pick the lower of those two values, and the lower of those two values is 12. So we'll update its beta value to 12. And it will pass those values down. And what's going to happen now? Try and have a think about what the alpha value will be after we've explored this path. What's the maximizing node trying to do? Is it altering beta or is it altering alpha? What's it trying to do to alpha? Is it trying to increase alpha or is it trying to decrease alpha? And if it increases alpha, what does it then need to check? Okay, so hopefully you can kind of start to remember that because it's a maximizing node, it's updating the alpha value and it's trying to increase it. It will increase it by comparing that value with the values of its children and picking the maximum. So this first child has a value of 17. So after exploring that, the alpha value will get updated to 17. And now what's happened? The alpha value has become higher than the beta value. And what does that mean? Well, it means that the highest value that this node will consider giving you is 12, because it knows that it can give you a 12 if it takes this path. So if there's a possibility for you to get something higher than 12 from this node, it won't give you that. We know that this node is going to be a 17 or higher, and we know that the parent of this node won't explore anything unless it has a value of 12 or less. So what happens here? Since the alpha and beta values have overlapped, we can now prune the rest of the branches of this tree. And that's what happens. Okay, what's going to happen next? It's going to return the value that it has given itself based on the children that it's explored so far. And what's this node going to do with it? Is it going to update the alpha value or is it going to update the beta value? What's it going to do? So since it's a minimizing node, it's going to try and update the beta value. It's going to compare its current beta value with the value of the child. So since 12 is lower than 17, it's not going to bother updating it. It's just going to stay the same. And it's going to pass those values which have stayed the same down to the third child. Now think again, what's going to happen to this alpha value when these children are explored? Are any of these branches going to be pruned? What needs to happen for the branches to be pruned? Okay, so the alpha value is currently -1. We're going to start exploring the children nodes and picking the maximum as the new alpha value. So since -7 is lower than -1, it's not going to update the alpha value. Now it explores the next node. Since 10 is higher than -1, which means that, remember that the alpha value represents the best the worst possible score that you can get in that position. But you're not going to consider taking something that's a -1 if you can get to a position which gives you a 10. So you're going to update it. You're going to remember that there's a path that exists that will give you a 10, so don't bother considering anything lower than that. And here we go, we've updated to give it a 10. Now, does this prune anything? Well, no, because the alpha and the beta values have not overlapped. The alpha value means that you can get a score of 10, and the beta value means that the lowest score that the minimizing node can currently force you into is a 12, and that's over here, this node here, because of the two currently explored nodes, this one's the lowest. So since there's no overlap, it's the best possible path that can be taken from this node so far, and the parent node is happy with you taking that path. There's going to be no pruning. It's going to check that. It's going to check this next child node, see that it's a 7, see that 7's not actually higher than alpha, and it will do nothing with it. Okay, what's going to happen here? This will return a value of 10 to its parent node. And since this parent node is a minimizing node, it will try and push down the value of beta. So it will compare 12 and the value that's returned from this child, and it will pick the lowest of those two to be the new beta value for this node. Here we go. And now, because the value of this node is 10, this is the value that will be returned to this parent. Okay, and what's going to happen here? Is it going to update beta, or is it going to update alpha? Well, what it's going to do is, because it's a maximizing node, it's going to be pushing alpha up. It's going to look at its current alpha value and the value that its child has passed up and pick the maximum as the new alpha value. So the maximum between -1 and 10 is 10. So it's going to update its alpha value. Now what does this mean? This means that it's discovered a path. So previously the best possible result from this node was a -1. But now we've discovered a path that our opponent isn't going to prevent us from taking because there's been no overlap. Like there was an overlap here. 17 would be better than 10, but there's no way that our opponent would let us take this path. So the 10 value represents a realistic value that we can actually attain, that our opponent isn't going to prevent us from taking. So this node is going to compare the current best realistic value with the new realistic value, and it's going to choose the maximum of those two because it's a maximizing node. And the maximum of -1 and 10 is 10. So that alpha value will be updated. And it will pass those values down again. Hopefully you're kind of getting the hang of it. I'll start to move a little bit quicker. Pass those values down. Okay, now it's going to compare. It's going to update it to 17. And then it's going to check -2, -3. It won't update in those cases because they are lower than 17. Going to pass 17 up. Since 17 is lower than infinity, it's going to bring the beta value down to 17. It's not going to perform any pruning because there's no overlap between the alpha and beta values. Now again, what that means is that in this part of the tree, the current best the current highest realistic score that the parent can have, that the parent can make, is a 10, and the highest score that this minimizing node will let you take is a 17, because 17 is the only one that it's explored. So there's no need to cut this off, okay? Because the way things are looking, it's actually looking like a pretty good option to go down this route. Okay, previously the best that we could possibly do is get a score of 10. But if we take this path, we're going to get a score of 17 or less. So we know that this minimizing node will pick the minimum of its children, so we know that it'll be 17 or less. But 17 or less still potentially is better than 10. Okay. So again, passes the alpha and beta values that it has down to its child, and then compares. Now what's going to happen here? Alpha's not going to be updated after exploring the first child. It's going to be updated to 15 after the second child, because 15 is higher than 10. And then it's not going to be updated after the third child. And again, there's going to be no pruning occurring, because there's going to be a small window between the alpha value of 15 and the beta value of 17. Okay. Now it's going to pass its current value, the current node value of 15, up to its parent. And because 15 is lower than this beta value, and the minimizing node is trying to push down the beta value, it will choose 15 as its new beta value. And it will pass those values down. Now what's going to happen? Alpha represents the best possible path that this root node can take. And exploring this path, it will give you a negative 11, and that's not better, so there's no reason for us to take this path, and there's no reason to update the alpha value. Now 13 is actually a better path, so it will update the alpha value. And then 12 is not better than 13, so it's going to stay the same. And there you go. This will pass up a value of 13, which will decrease this beta value. This will pass up a value of 13, which will increase this alpha value and will represent the best possible path that you can take, realistically. So it'd be great if we could get to this 17, but realistically, the best path that we can get is to this 13. Okay, and that's alpha beta pruning. In this particular tree, there wasn't actually too much pruned, but you can run into cases where this whole branch will be pruned, or one of these sub branches, maybe two of the branches will be pruned. And if this wasn't actually the root node, it would just pass this value up. It would pass the value of 13 up to a minimizing node, and if the value of 13 was lower than that node, it would lower than the beta value of that node, it would update the beta value of that node. Apologize for not finishing this off. And I hope you'll understand that the video I probably don't want to last for too long. You probably want to get some practice using this website if you don't understand it yet, which is perfectly fine. It takes a long time to understand this concept. Some of the tutors until recently didn't understand it themselves, so it's perfectly fine if you don't understand it yet. If you want to understand it though, try practicing using this website. Maybe rewatch this video, maybe watch other videos. Hopefully you're better equipped to understand the content of other, maybe more technical videos now. So yeah, I think maybe trying to code it was a bit too ambitious. It's stretching from the intuitive approach to the technical approach, which is probably too much. So thank you for watching, and I hope you learned something from this video. I hope you feel more confident in understanding the concepts, and I wish you the best of luck in coding up Minimax and alpha beta pruning as if you wish. So I'll see you later.